Probably okay. Okay, so before I begin, are there any questions that I can answer about anything related to homework stuff? I mean, I know it's, like I said, I'm giving you sort of the soft reprieve of you can turn it in now. If you have questions that you haven't answered yet that you want to, you are welcome to ask, in which case it's just on you to drop it in front of my office prior to me getting there tomorrow morning at 10:30. Just so you know, my office is in building 25 and it's 310. So there's a little brown box out front if you've never used these for homework before. So if you want to turn it in, like, I will not know if things get added to this folder, which will be sitting outside there with Math 306 written on it. If more homework goes in there between now and then, I won't notice. So are there any homework questions I can answer before we get started today? All right. So let's talk about direct sums today. That's what we're going to be after, is direct sums. And then direct sums is going to lead us to the idea of linear combinations and spanning sets. So the idea here is that, so there's an issue, right? So the problem is, so I'll say we're still working inside of 1C here. It's kind of the rest of kill somebody by throwing chalk. So the problem with, we could view it as a problem. The problem with the idea of taking the sum of two sets is it's not necessarily the case that every vector in here has a unique way of writing it as a combination of vectors in U and V. So the problem with U plus V is that, say, if I have a W that's contained in U plus V, there could be really secretly infinite ways of writing W as U plus V for U in U and V in V. Okay. So now lurking in the background here, even though we're not going to get to it for a while, lurking in the background here is the idea that we want direct sums to represent the idea of things being orthogonal to each other. So inner products are far away. We can't talk about orthogonality until we have inner products. But secretly, you should think of this would mean that these sets somehow overlap each other in a way, right? That there's overlap here. And with direct sums, what we want us to think about spaces is sort of not crossing each other at all, except at 0. Right? That's really what we're after with the idea of this, to clean this up so we have a unique representation of any vector in the sum. So, for example, if you let U1 be equal to, say, I don't know, x0, 0, where x is in R, and you let U2 be equal to 0, y0, y is in R. And you let U3 be equal to 0, 0, and it's like 0, 0, let's say ZZ. Something better than that. Let's do XX. 0. Where Z is in R. What's that? Oh, that? Sorry. I'll try to be neater with this. Okay, so we have 3 subspaces. We know these are subspaces of R3 because we have a line and a plane sitting inside of R3, right? These are subspaces. And if you take these subspaces and you take their set sum, so you take the set sum, the element 110 is definitely in that space, right? I mean, 110 is in U3. So you take that and you add it to the 0 here and you add it to the 0 here. And so one way of thinking about the element 110, which lives inside the sum, is that 110 can be written as 0, 0, 0, which is an element that came from U1, plus 0, 0, 0 as an element in U2, plus 110,
which is an element of U3, right? That's one way of showing that this element is contained inside that sum, is to show, well, I can get it by adding the pieces together to get it. The problem is I could do it lots of other ways. I could say, I don't know, how about we let, also 110 is equal to 1 times 100, that's an element of U1, plus 010, which is an element of U2, plus 000, which is an element of U3. So from an information standpoint, this is not good, right? I want to be able to say if it's important in a lot of applications to be able to say if something exists in a sum like this, it exists as a unique combination of vectors, not one where I can express it as a combination of these three and also a combination of three more. And in fact, an infinite family of ways I can make this vector out of these vectors from these three spaces. Okay. So I don't have unique representations of vectors. And that's so important in the structure of what we're going to say is when it is the case that this sum is unique, we give it a name, which is direct sum. Again, secretly in the back of your head, you can think about orthogonality is what we're going to deal to in the far future of direct sum. So here's the definition. If every vector in U plus V has a unique representation let's say for every vector W, if every vector W in U plus V has a unique representation, W is equal to U plus V for a, I guess I want to say we're with the unique here, has a U and V in V. So there's a unique U and a unique V, so the W is equal to U plus V. Then we say U plus V is a direct sum. It's a unique way of writing W as one unique vector from U and one unique vector from V. And we have a special symbol for it to indicate that this is the case. Right. U and then plus with a circle around it, V. So when you see that symbol, it means every vector inside here has a unique U and a unique V that make it up. If you have knowledge from 206 that you're bringing in here, you can think we're basically like hinting around the idea of linear independence and basis here. It's kind of where this is headed, this idea. Okay. This idea of unique representation is one of the features of a basis when we get there. Okay. So, okay, so for example, some examples here. If you have U1 x0, where x is a real number, and you have U2 0y, where y is a real number. In fact, yeah, then R2 is equal to U1 direct sum U2. You can think of this as like kind of the standard coordinate system, right? Okay, now this would be irritating to have to check. It would be extremely irritating, so the question is, here's a question we really like to know the answer to. In the same way that we wanted to know when a subspace was when a subset was a subspace, and I don't want to check all the vector conditions. So I have a theorem that says, well, instead of checking all the conditions on a vector space, let's check a smaller set of conditions, the closure conditions. Now our question is, when is U plus V direct sum. I don't want to have to check every single element in here is a unique combination of things from U and V. That would take forever and basically be impossible in any sort of abstract setting. Check every single vector U plus every single vector V to see if they're all unique. So what we're going to do instead is we're going to prove a proposition that says we're going to reduce this problem. We're going to reduce this to the case where instead of looking at every vector being having a unique representation, we're just going to look at 0. It's going to turn out to be the case that a sum is a direct sum if 0 has a unique representation. If 0 does, everything else will too. That's the content of our next proposition. Okay. So when do we go from a sum, all possible sums, to unique sums? It's going to turn out to be the case that if 0 can only be written. I mean, if 0 has a unique representation as elements in U and V, what does it have to be? 0 plus 0, right? I mean, it better be, and no, yeah, can only be written as 0 plus 0 and not with any other combination of vectors. For our example before, we had U1 being vectors of the form x, 0, 0, and U2 being vectors of the form 0, y, 0, and U3 being vectors of the form z, z, 0. It's pretty easy to see that I can write 0 a couple of different ways. I could put zeros in for everything and get 0, but I could also let this be 1 and this be 1 and this be 2 negative ones, right? 0 is equal to 1, 0, 0 plus 0, 1, 0 plus -1, -1, 0. That's from U1, that's from U2, that's from U3. As soon as I do this, I've basically blown it up, right? And if 0 has only a unique representation, then the important version of this is the converse direction. If the only way of writing 0 is as a list of zeros added together, then I've got a direct sum. Okay. Now, before I write the proposition down, I want to, this is one of these definitions you have to know. Somebody says U plus V are a direct sum. What does that mean? You should be able to say what that is. Okay. So definition, this is one of those important definitions that comes up in future arguments. Proposition says, suppose W subspaces of V, then U plus V is a direct sum if and only if. What did I say that? Yeah, sorry. Thanks. U plus W, yeah, these are the subspaces, right? So U plus W is a direct sum if and only if oh, even better than that, right? U intersect W. Not the empty set, because it can't be a subspace if it's the empty set. So it is 0. If we only intersect at the 0 vector, then that means the only way to write 0 is with piles of zeros. This means the subspace consisting of just the 0 vector. Okay. What's that?
Are those two statements synonymous?
Yes. In fact, we'll leverage this in the proof, right? This idea about 0 having a unique representation. I mean, what it means is that if you pick something in U, it can't be canceled out with the additive inverse in V, right? So the only vector that I could do that with is actually the 0 vector itself.
Okay. This one. So assume it's a direct sum. Assume u plus v. Let's make this more clear. Even though capital U's don't have tails, I'll put it on you and make it absolutely precise. Suppose that u plus w is a direct sum. Then, certainly, oh, I missed a step. This is the problem. I printed my notes and I forgot to bring them. So if v is an element of the intersection of u and v, this is what we're doing with this. If v lives in the intersection of u and v, so we're going to show that the only vector that can live in here is the 0 vector, right? So what's that? W. Jesus Christ. All right, I will. W. 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 Okay, if v is an element of the intersection of these sets, I even got it right in my notes and I keep messing it up. Okay, then 0 can be written as v plus minus v. And we're going to make a trick here, right? I mean, certainly it's the case that v has an additive inverse. Yeah? Okay, so we're going to use the fact that v is the intersection to say, well, if v is in u, then its additive inverse is also in u because it's a subspace, yeah? But also, if v is in w, then its additive inverse is also in w because w is a subspace. And so we're going to say v is an element of u. We're going to consider v to be an element of u and the additive inverse to be an element of, I got to write that down, w. So if v was in the intersection, then this statement would have to hold where, I mean, really secretly in the background, we're saying v and minus v. V is in u, so and also v is in w, and also minus v is in w, but also minus v is in u. That's being in the intersection means it falls in both categories, but I'm trying to force unique representation to hold. Right? So I'm going to imagine that v is in u and that minus v is in w. Now, u plus v is a direct sum, which means there's exactly one way to write 0, right? That's what it means to be a direct sum, is there's a unique representation of 0. So what do we say? Well, 0, I can think of one way to write 0. And that's unique because u plus v is direct. W is direct. It's a direct sum. There's a unique way of writing 0 as 0 plus 0. But what does that say about v and minus v? They must be 0, right? I mean, this is unique. This is the unique element of v, of u, that you can use to write 0 as a combination, but that means that v must have been 0. V is equal to 0 by uniqueness. So therefore, if v was in the intersection, it was the 0 vector, and that proves that direction of the argument. So u intersect w is equal to just the 0 vector. All right?
Can you re-explain?
Yeah, if you have a direct sum, so two things are true at the same time, right? You have a direct sum, which means any way I write down 0 as a sum of something in u and something in w is unique. This is in u and this is in w. So I have got one way of writing down 0, but it's unique because of the direct sum. On the other hand, I have another way of writing 0 down in terms of a vector v, which is in u, and a vector minus v, which is in w. But if I have two ways of writing something down, but they're unique, they must be the same, right? And so that means v must have been 0 and minus v must also have been 0. It's in the definition of direct sum.
Well, no, like saying that.
Oh, yeah, yeah. If you have two objects that are equal, but they're unique, they must be the same. Yeah, if the two, I mean, 0 has this representation, which is unique, and also 0 has this representation, which is unique. But if there's unique, there's just one thing. Here it's abstract, here it's named, they must be the same object. All right? Yep.
I might be missing something, but how does this prove that the U intersect W is the only thing inside it?
Because that element was arbitrary. If V is in that set, then V is the 0 vector, is what we just proved.
Or you say that V is the only.
Yeah, because pick me one that's not. Can you pick me a V that's not the 0 vector? And the answer is no, because any V you choose, this argument works for, right? You chose an arbitrary element in this intersection. And no matter what you started with, you end with the 0 vector. So that means there can't be anything else in there. Notice we said nothing about, I mean, you could do this by contradiction if you wanted. You could say assume V is not equal to 0, and then do the argument, and then V is equal to 0 will fall out at the end, and you can say contradiction, but it's the same argument. Okay, so when you're doing arguments like this, we start with an arbitrary condition on inclusion in the set, and we end with anything that I started with thinking no, I put no conditions on V except it was in that intersection, and I derived that it's equal to the 0 vector. So there can't be anything, it belonging to that set means you are the 0 vector. So there can't be anything else inside.
Can you explain the sentence if V is in U intersect W, then 0?
Oh, it just means that like if you have a vector that's in two sets, then it's in the first one and the second one, right? So if V is in U, then minus V is also in U.
Yeah.
And if V is in W, then minus V is also in W. So I'm just being cute and saying, okay, think about V as an element of U and think about minus V as an element of W. To be a direct sum means there's exactly one element from U and one element from W that add to 0.
Okay.
Right. And so I'm trying to take advantage of the fact that representations are unique in direct sums.
Thank you.
Okay, so the hard direction of this proof, if it has one, is the opposite direction. So let's do that. Okay, now it's actually not so bad. Now assume, okay. Here, you guys like arrows? There's the forward direction. Here's the backwards direction. In LaTeX, that's /R for right arrow. For the, did anybody LaTeX their work? I'd be curious to see. If anybody wants to like learn LaTeX in this class, I'd be happy to help. There's not a thread at all in that. Like if you want to learn some LaTeX and you want to practice it, you can do it in here. Okay, assume. Okay, so now what do we need for the other direction? Here we started by assuming that we had a direct sum and we showed that the intersection was the 0 vector. In the other direction, we're going to assume that the intersection is the 0 vector and we're going to derive the direct sum condition. So we're going to assume that U intersect W is just the 0 vector.
Is the question still the same for this direction?
What do you mean?
Suppose you the proposition.
The proposition is an if and only if, so we have to prove both directions. So direct sum if and only if intersection is 0. So we've shown direct sum implies intersection 0. Now we're going to show intersection 0 implies direct sum, and that will give us the whole proposition. Okay, so assume that our intersection is 0. So now suppose that we have U in U and V, V and W. How about W and W? An element of U and an element of V that happen to be the case so that U plus W is equal to 0. Let's just suppose we have two elements, one from U and one from W, that happen to add to the 0 vector. Okay, if we could show that these were both equal to 0, then we would be living in direct sum land. Okay, if U was equal to 0 and V was equal to 0, this would mean that we're looking at a direct sum. 0 has a unique representation, would mean that the thing we started with was a direct sum. So how can we show that? Yeah, so this would be like so all of this right here would be sort of like a want to show. This would let us use the fact that the representations of 0 are unique, right? If we could show that these two were 0, then we'd be finished, because it would mean that starting with two elements that add to 0 forces them both to be 0 would mean the only representation would be the 0 pile, right? 0 plus 0 plus 0, whatever, and that would force us to be a direct sum. Yep.
Shouldn't that be a W?
Oh my, geez, I could see the smile on your face as you set out to ask me that. Yes. If I pick two elements and they add to 0, we're going to try to show us that they both must have been 0. Okay. Of course, if that's true, if u plus w is equal to 0, then that means that u must be equal to minus v, or minus v, I even said it, minus w. U must be minus w, just by adding the additive inverse to both sides, yeah? Okay. Okay, oh, but look, that means u must also be in w. If u is the additive inverse of w and w is a subspace, right? So u is the additive inverse of w, w is in w, so u must also be in w. So u must be w. Oh wait, but that means u belongs to u and also w. We assumed u belonged to u. We've derived u also belongs to w, but there's only one vector inside the set. U intersects w. So u must be an element of u intersect w because it's in both sets. So u must be the 0 vector because there's only one thing in u intersects w. But what's the additive inverse of 0? 0. So w is also 0. So because u is equal to 0, this equation also forces w to be 0. Okay, so also, w is equal to 0 since u plus w is equal to 0 implies that 0 plus w is equal to 0. We know that w, I mean, that's the only vector that makes that true is the 0 vector. So w is equal to 0. And so that means that if we had a representation of the 0 vector, it was a bunch of zeros added together. Therefore, w direct is a direct oh my God, I did it again. Did I? People are smiling at me. Okay. Okay. Yep.
So when you say so u equals to 0, because that's what we assume.
We made the assumption that the only thing in the intersection was the 0 vector, right?
Okay.
So we've assumed the only thing in the intersection is the 0 vector. So I guess just as an aside here, implicitly, so I got asked if this is an equivalence here. So yes, it is the case that if 0, the actually proves this as a proposition, but the proof is pretty straightforward. If 0 has only the representation 0 is equal to 0 plus 0 plus dot 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 plus 0, then u1 up to um is a direct sum. So we use that in this argument, right? So I just want to write it down to codify it. If 0 has only a representation as a list of zeros, then the sum that it came from is a direct sum. Yep.
And sums of sets always have to be finite.
Sums of sets, yeah, for us, sums of sets are absolutely finite. If you want to get into, I mean, infinite sums of sets are things that you can consider, but the set theory that you have to build to do that is kind of nuts, because then you have to think about, was it a countable sum or an uncountable sum? Right. So there's like enormous amounts of topology and like idea of cardinality that comes up when you start going to infinite sets. Okay. Okay, that's nice though, because it means that we can always find a direct sum. That we can always find a direct sum by just checking the 0 vector or checking to see how the sets intersect each other. Okay. That's trivial actually, because then you could say that it's trivial. This idea of intersection trivializes a lot of problems. If I say, is this is, let's say, a set of things that look like x0, where x is equal to r, plus the set of things that look like 0y, where y is equal, y is an r. Is it direct? You could say to yourself, okay, well, everything that looks like x0 intersected with everything that looks like 0y. The only intersection between these two sets, here's the set of points that look like x0. Here's the set of points that look like 0y. Where do they cross each other? At the 0 vector. The chalk is commenting on the thrill of this particular proof, I suppose. Right. So yeah, basically you should think of direct sums as sets that just cross once. And yeah, we can't use the empty set. The natural thing to think is, well, why 0 and not the empty set? Remember, we showed the empty set is not a vector space, right? Because the empty set doesn't have a 0 vector inside of it. Okay. So now we come to the foundational chapter for all of linear algebra. And I am going to, I'm going to write this on the board. Learn these definitions. Learn the upcoming definitions. To the point where if I come in here at the top of class and I hand a piece of chalk to somebody at 3:10 and I say, go write the definition of linear independence on the board, every single person in here should be able to do that. I'm not actually saying I'm going to do that, but I could. In fact, if you wanted me to, I could torture you with any sort of cold calling you wanted. I could assign you all numbers and say, number 31, tell me what a spanning set is. This is a strategy that's recommended in some contemporary pedagogy. But we'll see. That seems kind of mean unless you voted for it. Like you'd have to enact it on yourselves. But that's the sort of level of command I want for this. I want that kind of recall. Like you should think on any day I could come in here and say, what does linear independence mean? And you should be able to write it down. Okay. Okay. So the study of linear algebra is built out of things that we construct using linear operations. So linear algebra is built from linear operations. So what do I mean by that? A linear operation, I just think like if I add two things, I stay in the same line. And if I multiply by a scalar, I stay in the same line, right? So linear means I'm not squaring things. I'm not taking square roots. I'm not multiplying. I want to combine things in a way that's compatible with linear maps, linear functions. So we're going to make a definition. This is sort of our first foundational definition here, which is, let's let V1 up to Vm be a list of vectors. A vector space V. When I write V, I'm going to follow Axler's thing, which he just goes over to say, every time I write V, I mean let V be a vector space because I'm tired of writing let V be a vector space all over the place. So if I write V, I mean vector space. Okay, the other thing you might think is, well, you wrote a list, but you didn't put parentheses around the outside of it. It's because it's annoying to write lists of vectors and put parentheses around the outside because it confuses a list of coordinates with a list of vectors. So what he means when he says a list of vectors is a finite set of vectors arranged in order with commas. That's it. He could put parentheses around it and it would mean the same thing. Okay, he just means an ordered finite list. Infinite dimensional linear algebra is awesome, but we're not going to get there probably. A linear combination of the list is A1 V1 plus A2 V2 plus AM V M AM VM, where the AI are scalars that come from whatever that field happens to be for the vector space that you're on. So a linear combination of a list of vectors is multiply them all by different scalars and then add them all together. Different or the same, right? You're going to pick a bunch of scalars, multiply by the vectors, and add them up. So for example, 2v1 plus 3v2 is a linear combination shopping cart? What is that?
1 and V2.
Okay. It is a shopping cart. Okay, and also I'm carrying 3/8 plywood. Okay, it is important to note here that these will always be finite, right? Some people might say finite linear combination, but they mean for us linear combination. Now, amusingly, I have another example of linear combinations. So maybe you've seen this if you've taken differential equations. Cosine of x is a linear combination of e to the ix and e to the minus ix. Functions, these are complex valued functions. They're totally legal vectors, right? These are legal vectors in the world of complex valued functions, e to the ix and e to the minus ix. Why do I say it's a linear combination of those things? If you've ever wondered in the past why cosine of x has derivatives that repeat themselves forever and almost no other function does, it's because secretly in the background, there's no such thing as cosine of x. Cosine of x is equal to 1/2 of an e to the ix plus 1/2 of an e to the minus ix. Yeah. And the reason that has infinite derivatives is because these are exponentials. This is one of the behind the curtains sort of things. Yeah, so linear algebra works on function spaces and it lets you do stuff like this, right? Cosine of x is nice because if you take 1/2 of an e to the ix and you add it to 1/2 of an e to the minus x, you get cosine. This is not an example that will come up much in this class, but it's cute. Anyway, part of the point of showing you examples like that is to show you this, all of these ideas, even if we're studying them at finite dimensions, hook into much higher level mathematics, right? Linear algebra actually sits behind a lot of calculus as well. Okay, important definition 2. Okay, this one, absolutely hammer this one into your heads. The span, probably ringing some bells from 206 here. The span of a list V1 up to Vm is the set of all linear combinations of V1. So the span of a list is the set of all the possible linear combination of those things. It has a special notation. Span of V1 up to Vm. If I want to write it in set notation or set builder notation, it looks like the set of all objects that look like A1 V1 plus A2 V2 up to AM VM, where A1, all of the AIs come from the field. It's the set of every possible thing that looks like this. Make sense? Yep.
How does like span and linear combinations relate to direct stuff? Like,
Okay, so the direct sums are so that's an excellent question. Okay, so it turns out to be the case that the way that these that you can chop a span up into pieces that have direct sums is if you sneak in things we haven't talked about yet, like linear independence. So if I have a span and each vector has a unique representation, then to say that this set is a direct sum of the spans of each one of these individual vectors, that only happens if these things turn out to be linearly independent. Okay, so I'm using ideas I haven't discussed yet, but yeah, that's all direct sums and linear independence and span all kind of sit together, and the idea of a basis is going to come in on that ground as well.
So spans a set of vectors. then?
It's a set of vectors. In fact, it's better than a set of vectors. Because what does a subspace need to be a subspace? Has 0 inside that set? Well, yeah, I could choose all the AIs to be 0, right? So the 0 will live inside that thing. Is it closed under addition? Oh, look, I've carefully set it up to be closed under addition, right? Because two things in the span, if I add them together, will still be linear combinations of V1 through VM, right? So by definition, this thing is set up to be closed under addition. Will it be closed under scalar multiplication? Sure, because of the distributive property. Yep.
You kind of answered it, but does the set F, does the field have to contain 0?
Does this, well, every field has to contain 0, right? Yeah, so like remember F here, F can, for our purposes, F is either C or R always. And C or R always contain 0, okay? So basically we have rigged this thing up exactly so it's precisely what a subspace is. It's basically going to turn out to be the case. And we probably don't have time to prove it today. Yeah, we don't really have time to prove it. So I'll do a little bit more description first. What we're going to prove is that this is the smallest subspace containing V1, V2, V3 up to VM. You can't get a smaller one. This is the smallest. This is like basically custom built to be a subspace that contains all of these vectors. And it's the best one. In the sense, I guess, of smallest is best. You should believe, though, that this is a subspace, right? So you should believe. And in fact, I would argue, when I say you should believe, that's secret math professor language for you should prove. Oh, don't give me that expression. Sucking on lemons in here or something, right? You should believe / you should prove. Or read Axler's proof, although this one is actually more fun to do on your own, I think. You should believe that the span of a set of vectors is a subspace. And you should not just believe it's a subspace, you should believe the definition was set up to make sure that it's a subspace, right? Okay. Now I'm gonna hit you with a bunch of words that we're going to be talking about over the next bit here. But I guess the first thing, I don't really want to state the theorem and prove it. I'm going to do one more example here, which I'm going to ask you, what is the span of the vector 1, 0, 0 and the vector 0, 1, 0? I heard a concrete vector with numbers. I heard something with variables. Okay, so the first thing you would say is, okay, so it's A1 times 1, 0, 0 plus A2 times 0, 0, 1, but for any choice of A1 and A2. So it's the set of all of these guys where A1 and A2 are in the field. So which you can reduce to things that look like A1, A2, 0. Yeah, it's the XY plane and XYZ coordinates, right? So what I want you to think with span, the whole point of an example like this is to remind you the span is a linear space, right? So the span of a set of vectors is going to get you a plane-like object out. And every time you put another vector in, you're adding another direction that the plane can run in, assuming it points in a different direction. Okay. What's the span? You know, I'm not going to ask that question. I lied. I was going to ask something tricky and hard, and I've changed my mind about it. What happens if there's extra vectors inside? So what if I wrote this? I mean, is the span all, this is two vectors came in and this sort of space with two choices to make came out. What's the span of the vector 1, 0 and the vector 2, 0? Yeah, because if you have A1 times 1, 0 and you add it to A2 times 2, 0, are you ever going to pick up anything in the second slot? Well, no, there's only ever 0 there, right? And the idea is, well, if this is just A1 plus 2A2 comma 0, can I get any number I want in the first slot? Okay, so really, this is just a one-dimensional, sorry, one dimension. I haven't talked about dimension yet, but this is defined by just a single, it's everything of the form x comma 0. I can get these, but no more. Right? It looks like there's two parameters here, but they're just modifying the same number. So this is kind of like the idea, we're going to sneak the idea of dimension in here by when we talk about like the number of vectors it takes to make this is going to get all tangled. The smallest number of vectors you can use to describe a set in a span is the dimension of the span. Yep.
That's synonymous with like rank.
Rank is actually a property of matrices, right? But if you consider a set of vectors as a matrix, then you can think about it as having rank. Yeah, so rank, you can also think about rank as the number of linearly independent vectors. But again, we're using all these words I haven't defined yet, right? This is what we're building towards. Okay, span should be an idea you are absolutely comfortable with. This is like one of the great rocks that the ship of linear algebra 206 goes down on, right? It's like you do linear algebra 206 and it's all computing with matrices, and then you crash into the shore because all of a sudden you're asked to prove something involving span, and everyone goes, oh my God, I don't remember what span means. Like, I just write something down. Maybe there's some vectors and some numbers and I'll add them together. I mean, I've taught 206 before, so I know what it looks like. Okay. Yep.
Span has nothing to do with the fact that it's like a unique.
There's no uniqueness
No
here.
uniqueness.
No uniqueness. Okay.
Clarify.
So the word that the word that's going to come in for the future with uniqueness is basis, right? If the set of vectors is linearly independent, then that set of vectors is a basis for its span. Right? So uniqueness is important. We're going to get there, but this has infinite representations of any vector inside here. And that's the problem, is that this isn't uniquely represented as a linear combination. All right. Get these. I know there's going to be a lot of words flowing around here the next couple of days. Make sure you keep these things straight, even if you have to index card them and practice them. All right. Get these definitions down. See you guys tomorrow. And I guess we're not having a Thursday holiday this week.